Hello, Algebra 2. We're going to continue looking at more sequences today, and instead of formulating the formulas for certain kinds of sequences purely creatively, we're going to begin exploring some specific formulas that we can use to make that process easier. So instead of thinking about notations of sequences, we're going to begin today by thinking about a couple specific types of sequences. So I really want to make the point again, and I'll just write that down up in the top here somewhere, that there's a difference between notation or form. So we have notation, and that's the form or way you can express a sequence. That is not the same thing as a variety of sequence or a type of sequence or a kind of sequence. So let's make sure that that's clear to us. So we're going to be looking at two specific types of sequences today. We're going to be looking at linear sequences first of all. So in sequence land and in math in general, it's very common to refer to something as arithmetic. So an arithmetic sequence is basically just a line. So when we were working with the entire set of real numbers, we looked at lines mainly with the slope-intercept formula, y equals mx plus b. So in sequence land, you can pretty much just replace the y with the output a sub n of the sequence, and the input x, which is a real number, with the natural number n. So in sequence land, the main difference here is that the slope, when you do m back in the day, you look at change in y, or the y's over the x's. That of course means change, that Greek delta. So you look at the y's over the x's when you're used to slope. In sequence land, the change in x is nice. It's always the same because remember, sequences work on the natural numbers 1, 2, 3, 4, 5. And I know sometimes we've kind of worked with indexing a series with 0 and stuff like that, but let's not get into the subtleties too much. But that's the domain. So the change in x between those is always going to be 1 no matter what. The change in y could pretty much be anything, but the change in x and the slope is always 1. Alright, so the thing that's really going to make sequences, I think, easier for you to do and recognize the explicit pattern is using this formula right here. So this is something you definitely want to memorize. So in this formula, a sub n is the form for an arithmetic sequence. So this guy right here, just think of it as two ingredients. A sub 1, I think you should already know, of course, is the first term, or the first thing in your list, and D is what we're going to call, we haven't seen that yet, D is what we're going to call the common difference. So we'll look at some common differences in a second, but D is the common difference. Okay, so we're going to look at two examples of arithmetic sequences. These are the same kinds of things we've been seeing, but we are going to do them kind of with this formula, formulaically, instead of creatively. So I just picked this totally randomly in class. People were like, where'd you get the 73 from? Well, I picked 73 totally randomly, so we're going to figure out the formula, the explicit formula for our sequences, and then we're going to find the 73rd term. I picked that totally randomly, so random. Alright, so here is a sequence. Is it arithmetic? Well, I think it's going minus 4, minus 4, minus 4 every time. So if it does that kind of plus or minus action every time, that is D. That's what I'm calling the common difference, if you're adding or subtracting by the same thing each time. Of course, the first term is easy to see, so if you know it's an arithmetic sequence or you suspect it is one, see if you can find a common difference and then go, okay, I know the formula because I've memorized it. It's the first term plus I count n minus 1 d's from that first term, and I just plug in the ingredients. The first term was 85, n minus 1 is n minus 1, and for us d was negative 4. So that means a sub n is that. So all I have to do now is distribute and simplify, and I'll have my nice linear sequence. So there we go. I'm going to have 85 minus 4n plus 4. So that's going to be negative 4n plus 89 if I combine my like terms. And there we go. There's a nice formula for our arithmetic sequence. So let's find the 73rd term. Since I asked for a term, the 73rd term is going to be negative 4. Plug in 73, add 89, and you're good to go. I'm going to say negative 4 times 73. No, I'm not sure about that. Well, can we do it without our calculator? Let's try. Negative 4 times 7 is 28, so that's negative 280. And then we've also got negative 12 plus 89. I think we can put 280 and 89 together, can't we? Isn't that going to be a negative 191? And then we've got minus 12, so that's going to be a negative 203, I think. There we go. I managed to not use my calculator there. Arithmetic action. Good to flex your arithmetic muscles if you can. I'm not the best at it either, so I have to practice. All right, so let's look at another arithmetic example. Let me move this out of the way. All right. So the second one is supposedly also arithmetic. Let's see, what does it do? It looks like it's going down by 0.3. Yeah, it's going down by 0.3 each time. Do you see that? Okay, so that's D on this one. So then we say, all right, write down my formula, first term. I'm going to count n minus 1 d's from that to have my explicit formula. So we're going to have negative 2 plus n minus 1, and then we're going to have negative 0.3 there. Okay, let's simplify. So distribute that negative 0.3. Have that, and then we'll have a positive 0.3. So a sub n is going to be, what, negative... Oh, is it going down by 0.3? I think it's going to be plus. Isn't this plus? I think I have a little mistake there. I think it's going up, isn't it? Yeah, it's getting closer to positive land as we go. So this should have been positive. I think I'm going to have to fix that. Let's make this negative 2, and then this should have been positive, right? Positive. And this should have been negative. So it's negative 2.3 plus 0.3n. There we go. There is our explicit formula. And then if we want to do the 73rd term, let's just find a spot over here and do it. So this is for number 2. And it's going to be negative 2.3 plus 0.3 times 73. Since this is getting closer and closer to 0, this should be a positive answer, right? So it's going to be, what? I think it's 19.6. I put it in my calculator. You can do that, of course. No need to waste time there. All right, so let's look at the other kind of sequence shortcut formula. So how you can think of things like this formula right here for one other type of sequence, not notation, type. So an exponential sequence is one that's equally common to an arithmetic sequence, except if it's exponential. We usually thought of exponential functions kind of as growth functions. We had two varieties back in our library of functions. We had growth ones, and then we had ones that decay. You know, we had things that looked like this for growing exponential functions, and then we had ones that looked like this for decaying exponential functions. You know, just to review a little bit there. In sequence land, they're not called exponential usually, they're called geometric functions. So why do you need to know all of these vocabulary terms? Well, just last week in my AP European History class, we were actually talking about Thomas Malthus. He was an 18th century economist and social theorist, and he had this idea about how he was worried about population growth because population growth is a geometric phenomena while food production is only an arithmetic phenomena. And so to really understand what he's talking about, precisely at least, let me get rid of this cat that I have here, we'll see if that works. To really understand what Malthus was talking about back in the 1800s, 1700s I think actually, you have to understand these terms geometric and arithmetic to understand. So it's really important to work with the vocabulary. So the nice thing is you really only have to remember one formula too. So the geometric formula is right here for any time you recognize something might be multiplying for each step or dividing for each step. It works almost exactly like the arithmetic formula. The R here is instead of a common difference, it's called the common ratio, or thing you're multiplying by. So it's the multiply, my cat does not want to go away, or divide factor. So let's look at a couple things that look like they're geometric or exponential sequences. I think number 3 is pretty easy to see. What's happening from 7 to 21 to 63? Think about it for a second, and I think you're going to know that it's multiplying by 3. So that's what we call R. We call R the common ratio 3. So let's write down our formula. So then we say, okay, if we think it's multiplying or dividing, I go a sub n is the first term, and I multiply by r n minus 1 times from there. It's the same thing as up here where the nth term is the first term, and I add n minus 1 d's. Exactly the same kind of concept. Alright, so let's plug in our information, our ingredients, and get going. So the first term is 7, r was 3, and n minus 1. You can't simplify here. In my class today, we had a few people who were asking me, and I think a lot of people had this on their minds, could you simplify this to something like 21 to the n minus 1, or maybe 21 to the n if you like have a 1 here and you add the 1 and negative 1 and just get n? And the answer is no, you can't do that. Remember from basic algebra 1 that if you have the same base, like 3 squared, and then you multiply that by like 3 to the 7th, that's going to be 3, 3, 3, 3, 3, 3 a lot of times. In fact, there's 9 3's being multiplied, so you can add those exponents. But if you had something like 2 to the 8th times 5 squared, it's not like you can go that's 10 to the 10th. Because, of course, I think from our power tables, we should know 2 to the 8th. What is that? 2, 4, 8, 20, no, 16, 32, so forth and so forth and so forth. Maybe we should just pull up our calculator here. Let's go grab it. So 2 to the 8th power. Let's just do it. 2 to the 8th power. 256, yeah. Just like base 2 computer stuff. So that's 256 times 25. Is that equal to 10 to the 10th? That's 10 billion. Yeah, or no, 10 to the 9th would be 10 billion. This is 100 billion. 100 billion isn't 256 times 25. This is definitely not true. So let's just get that out of there. That's terrible logic. Unless you have the same base, you can't be doing this kind of stuff. So what was the question I had in class over here with the green idea? It's really not going to work because base 7 and base 3 aren't the same. When you have exponents in those kind of situations, you really can't simplify, at least not that way. There might be some other options which we could pursue at a higher level, but I think this is good enough for us for now. So there's our sequence. We didn't have to do anything. We just had to pick the first term, figure out r, and we're done. So if they ask us for something like this one randomly, asked for the 9th term, okay, we say, all right, plug it in and get it. So it's 3 to the 8th. So it's going to be 7 times a big number. Just go and grab our calculator one more time. Clear it. We're going to have, what do we have, 7 times 3 raised to the 8th. So that's a big number, 45,900. So just leave that alone. And 45,927, I think it was. So there we go. So on this one, I think it's a good idea for you right now to pause the video and see if you can figure out the geometric form to that. So go ahead and pause. Alright, so if you've thought about it, how did you get r on this one? R is a little bit trickier. So r is going to be trickier to obtain on this guy. So if you think, though, that you're like, I think it's multiplying or dividing, I'm just not sure by what. The great thing is you can figure that out easily. Let's go back to number 3 for a second. It was pretty easy to guess that r was 3 here. Because if you weren't sure, though, you could always confirm it. R is always going to be a ratio of successive terms, like the second one over the first one, the third one over the second one, the fourth one over the third one. It's really always the current one over the one that was before it, if you think recursively. And that has to be the same for every ratio if it's the common ratio r. So back here it was easy to see that 21 over 7 is 3. Just like 63 over 21 is 3, etc. It's always going to be this 3. So let's apply that same logic to our problem over here where we're not really sure what r is. So over here we're not really sure. It might be a 10th or a 5th or something like that. But let's see what we got. So let's try these two terms. It doesn't matter where you do it. If it's truly multiplying or dividing, you've always got to have the same ratio. So I'm going to go that one over the previous one. That's a copy dot flip multiplied by the reciprocal, right? So that's going to be negative 5/10. That's negative 1/2. So just to confirm if it looks like I'm right here, I'm going to go, well, let's try it in another spot. Perhaps let's try these two instead. So then we have negative 1 over 20 divided by 1/10. So that would be negative 1/20 times 10 over 1, which is negative 10/20, which is negative 1/2. Yes, it does look like this is indeed multiplying by negative 1/2 each time. So let's get our formula going. We've got our negative 1/2 for r, and we're ready to go. So that says r is negative 1/2. So that means our sequence is going to be the first term multiplied by r n minus 1 times. So that's going to be 2/5. Negative 1/2 we found was r to the n minus 1. So if we want the ninth term, like they asked us, just kind of randomly in this example, that's a pretty sloppy 5. That's a worse 5. Yes, we can do this. So 8th power, so that's going to be 2/5. Negative 1 to an even power is 1, and 2 to the 8th power. Didn't we just do that over on this problem a second ago? 2 to the 8th power, wasn't it 256? I think it was. Oh, and 2 and 256 will reduce. This is really going to become 1 over, we've still got the 5, and 128 is 256 divided by 2. So put that in your calculator. I think it's 640 because I just did it a moment ago. All right, so let's move on, and you can try a little bit of practice now. So move on to the back side of your note sheet, or if you're just watching the video and don't have this sheet, go ahead and pause it and see if you can identify each one of these sequences. None of them are too tricky. See if you can identify, are they arithmetic, are they geometric, or are they something else that we're not focusing on in this lesson? And if they're arithmetic or geometric, if they're arithmetic, do D. If they're geometric, find R. So go ahead and pause the video and see what you can get with those. So if you've paused the video and already tried these sequences out, let's see what we get now. So each sequence, let's go through them one at a time. This one looks like it's going down by 7, then down by 7, then down by 7. So this one looks arithmetic to me. So I'm going to say arithmetic, if I can write. And I think D is the negative 7. Okay, this one looks like maybe down by minus 90, or I could divide by 2, and then it's minus 30, so it's not arithmetic, and if I divide 90 by 2 I would get 45. So it doesn't look like it's geometric either. I think this one is some kind of other pattern. We could probably write it down without too much trouble, but it's neither arithmetic or geometric. Alright, let's look at this one. Fraction. Maybe I'll look out here. 5 times 5 is 25. These all look like powers of 5. Oh, and this is even 5 to the negative 1, and this is 5 to the 0. Yeah, this is totally arithmetic. I think R is, I shouldn't have said arithmetic. It's totally geometric with R as not 3. What am I thinking? I'm multiplying by 5 each time. This has a 5. Alright, over here, let's see, what are we doing? 20 to 5. Is this division? Maybe we should check. Divide by 4 and you get 5. If you divide 5 by 4, do you get 1 1/4? 5/4? I think that's yes. So this is totally also geometric with R as 1/4. Okay. Let's review from the last lesson now, because the last thing we want to do in this lesson is add one more shortcut formula. So we talked about Gauss last time and a shortcut formula, and we talked about these other ones as well. So this, remember, just says add C up a whole bunch of times. In fact, you want to add C n times. So what's the formula for that going to be? Well, you're just adding C up a whole bunch of times, so that's going to be n of these c's. Remember where the n is coming from here. This is Gauss's formula. Remember, it goes 1 plus 2 plus 3 plus forever out until n. I shouldn't say forever because it's not infinite. So the formula for shortcutting a sum like that, a finite sum, is to use Gauss's formula, which yesterday we learned is the end index times that index plus 1 over 2. Alright, so there's our formula there. We didn't get into this one too much yesterday because we're just going to continue to use some of these, but we do want to memorize at least these three. So this one's going to be that n times n plus 1, just like Gauss, except then we have another little factor right here, 2n plus 1 over 6. And that's for when you're adding up the squares. 1 squared plus 2 squared plus 3 squared plus dot 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 plus stopping at n squared. Okay, so which ones of these are useful if you're trying to look at specifically arithmetic sequences? Well, think about it. Arithmetic sequences would be something like this, right? They'd be plus, get rid of that plus. Arithmetic sequences would have the form something like m n plus b, where this is a constant just like c, so we need this guy, so we'll say formula 1 up there. I didn't give it a number, but you get the idea. And I think you also have the variable here is n, so if you have n, even if there's some specific slope number that you can factor out, you could just put that m right here, and this would kind of be like the n. So 1 and 2 are the formulas for lines. This would be for some kind of parabolic sequence, which we have a nice shortcut for as well. What I wanted to do today, though, and the last thing in this lesson, is to add a shortcut that we want to know. And this is a little bit ambitious to memorize, but we'll at least memorize it for now, and hopefully you can find it later if you need it, because you'll have some experience. We want to figure out the formula for shortcutting this finite sum of, what is this? This is the form of a geometric sequence. So the shortcut for that, which we sometimes call the sum with s of the first n terms, is this formula over here. So this is what you want to remember. So which one of number 5 or number 6 is amenable, or which one of 5 or 6 can we use this new shortcut formula on? Well, which one looks like it might fit the geometric form? So which one looks like it might do this kind of thing? I don't think this one does it. In fact, this looks like a line, doesn't it? Like there's the mn plus b. So this is one of the old ones. We'll do that in a sec just to review. But this guy, I think, has a r to k minus 1. That's just like that. There's no a1. Oh, but I could just put a 1 there and I'd be good to go. So the formula says it's equal to a sub 1, which for us is 1, kind of boring this time, times 1 minus r here is 1/3, and that needs to be the n power, the n being this top number. So I'm going to put that right there. That's all supposed to be over 1 minus, again, r. So r is, again, 1/3 for our sequence. So most of the time you can't just erase this thing out here, but for us we really don't even need to write the 1 if it's just 1. On the bottom is pretty easy. 1 minus 1/3 is 2/3. And on top we might need to do a little work. So I'm going to try to not use my calculator once again. 1 to the 7th is just 1. That's easy. 3 to the 7th. Do we do that with our power tables? I think in the last video lesson actually it was in there. So let's just count by 3. So we've got 3 times 3 is 9, times 3 is 27, times 3 is 81. And if you're watching the video and you really don't know these numbers very well, my class spends the beginning of the year really memorizing the powers of 2s and 3s and all the way up to 8s and 9s at least. They know their 2s and 3s pretty high, and we take some quizzes on those. Really useful to know these in algebra and further math. Anyway, so 3 to the first is 9, 3. 3 squared is 9. 3 cubed is 27. 3 to the 4th power is 81. 3 to the 5th power is 243. 3 to the 6th power is 729. And that's about as far as my class is supposed to know. So then you might need to use your calculator. In the last lesson, though, I think we did this one, so it was 2187. And I think that is the 7th power of 3 that we need right here. All right, You could also, of course, stick this in your calculator at this point. I'm going to try to do some common denominator math because at this time in your math career, whether or not you're too great at fractions, you need to start working with them and get better at them because you need them in calculus. So let's see. I think the common denominator here is 2187. So really, I'm just going to multiply and make this be 2187. If I put this red thing here, though, I have to compensate, of course, or otherwise it's illegal. So I'm going to put 2187 on top, too. And let's see what we get. So we're going to get everything's over 2/3. That's going to be 2187 minus, there was a minus right there, minus 1 over the common denominator. Now this is another copy dot flip. 2187 minus 1 is 2186. 2187. Copy dot flip. And simplify. I think this is a power of 3, right? It's 3 to the 7th. Take away one of the 3's, and you'll get 2186 over 3 to the 6th. Oh, and I had that right here, right? So that's going to be 729 times, now this is gone, and I reduced this. So now I've got 2186 over 2, that's a 7. And I think that is going to be 1,000. 100 divided by 2 is 50, and 86 divided by 2 is 43, so it's going to be 1,093 over 729 times 2, I don't know. That's pretty good right there. We could put it in our calculator if we wanted it further. So if you want, you could probably stop the video now. This is just going to be another example of an arithmetic shortcut formula using Gauss and stuff from up here. So I think we've got 9 a whole bunch of times, 1,500 times in fact. That's using this bad boy. And then I think we've got 8 times n. We're going to have to use this guy as well. So what's that going to be? It's going to be, we'll add on 8 times over 2, n is 1,500 times 1,501. There's Gauss's formula in action again. If you're watching the video and you want to see more in detail and the story about where this formula comes from and its derivation, you can go and watch the previous video in this series. Anyway, we're going to finish up here though. 9 times 15, what is that? Maybe we should just go to our calculator. Before we do though, I think I'm going to reduce this to a 4. So let's go pull up our calculator and finish up for today. So let's see, where is my calculator? There it is. So we've got what that we need to do? We have 9 times 1,500 plus 4 times 1,500 times 1,501. Alright, so there we go. A pretty big number that would have taken a long time to add up if we just started plugging in 1, 2, 3 all the way to 1,500. So what do we have there? Oh, I lost it. I'm going to have to memorize it here. 9019500. So 9019500. I think that's what they had, so that looks like 9 million and some is what that sequence, that linear sequence, sums to from 1 to 1,500. Next week we'll learn how to program this with a loop using Python. I'll see you then.